Proxima B represents a celestial body whose dimensions closely approximate those of our home planet. This singular characteristic alone captures the undivided attention of the scientific community worldwide. When astronomers encounter exoplanets possessing terrestrial-scale proportions, speculation naturally turns toward the possibility of Earth-analogous environmental conditions existing within these distant worlds. However, caution must temper enthusiasm. Proxima B maintains orbital patterns around a stellar object fundamentally different from our solar system's central star. The planet's host constitutes what astronomers classify as a red dwarf, specifically designated Proxima Centauri. This stellar formation demonstrates significantly reduced mass, diminished surface temperatures, and substantially decreased luminous output compared to our Sun's characteristics. These stellar properties prove critically important since the nature of a planet's host star directly influences atmospheric dynamics, thermal regulation, and the fundamental potential for biological sustainability. The truly captivating aspect emerges from Proxima B's positioning within what researchers term the circumstellar habitable zone. This represents the orbital region surrounding any star where surface temperatures permit liquid water maintenance, neither excessive heat causing vaporization nor insufficient warmth resulting in perpetual freezing. When investigating potential extraterrestrial biology, liquid water availability consistently represents the primary prerequisite for consideration. Nevertheless, interplanetary relocation remains premature. Proxima B presents formidable environmental obstacles that challenge habitability assumptions. Primary among these concerns involves probable tidal synchronization, a gravitational phenomenon ensuring one planetary hemisphere perpetually faces the host star while the opposite hemisphere remains locked in continuous darkness. Consider existence on a world where one geographic region experiences constant scorching temperatures while the opposite territory endures permanent sub-zero conditions, hardly conducive to comfortable habitation. Compounding these challenges, Proxima Centauri exhibits volatile stellar behavior patterns. This red dwarf periodically releases catastrophic solar eruptions, massive energy discharges capable of impacting Proxima B with devastating force. Such coronal mass ejections potentially strip away atmospheric protection or render surface conditions lethally radioactive for any potential biological systems. Despite these formidable complications, the scientific community maintains intense interest in Proxima B. The rationale stems from its status as among the nearest Earth-scale exoplanets discovered to date. Additionally, theoretical models suggest possible liquid water reservoirs might exist within specific planetary regions. These factors combine to establish Proxima B as a premier candidate for extraterrestrial life investigation beyond our solar system's boundaries. Understanding red dwarf stellar systems. Initial impressions might suggest red dwarf stars lack compelling characteristics. These stellar objects emit minimal luminosity, possess modest mass compared to the spectacular giant stars featured in popular astronomy documentaries, and certainly would not receive recognition for dramatic cosmic phenomena. However, such superficial assessments prove misleading regarding their astronomical significance. Red dwarf stars constitute the most abundant stellar type throughout our galactic neighborhood. Random spatial coordinates would statistically favor proximity to red dwarf systems over any other stellar classification. These formations demonstrate compact dimensions, subdued radiance, and exceptionally conservative nuclear fuel consumption patterns. This methodical energy expenditure enables continuous stellar activity spanning billions, occasionally extending to trillions of years. Extended stellar longevity proves astronomically significant because orbiting planetary bodies receive substantial temporal opportunities for stable existence, a favorable condition for potential biological development processes. Since red dwarf systems operate at reduced temperatures compared to our Sun, their respective habitable zones, regions permitting liquid water stability, occur at dramatically closer orbital distances. This positioning becomes relevant when examining worlds like Proxima B. Proxima B maintains orbital mechanics around Proxima Centauri, classified as a red dwarf system, while fortuitously positioned within the stellar habitable zone boundaries. Consequently, despite the host star's diminished luminosity, planetary surface regions could theoretically maintain temperatures supporting liquid water reservoirs, and wherever water exists, biological possibilities emerge. Examining Proxima Centauri's specific characteristics reveals minimal visible light emission, approximately 0.05% of our Sun's optical output. This represents negligible illumination levels, yet Proxima B's close orbital proximity enables reception of roughly 70% of the infrared radiation that Earth receives from solar sources. Therefore, while traditional sunbathing would prove impossible, the planetary environment might sustain adequate thermal conditions for habitability considerations. However, significant complications arise from Proxima Centauri's classification as a stellar variable, specifically a flare star prone to temperamental behavior. Periodic stellar outbursts can increase luminosity by factors exceeding 100 times normal levels, simultaneously bombarding surrounding space with intense radiation doses. These sudden energetic emissions could prove catastrophic for any biological systems attempting establishment on Proxima B, potentially disrupting atmospheric chemistry and creating hostile surface conditions incompatible with life processes. The BLC-1 signal mystery. During 2020, researchers affiliated with the Breakthrough Listen project detected an anomalous radio transmission originating from Proxima Centauri's directional coordinates, representing the nearest stellar system to Earth. This signal, designated BLC-1, generated considerable scientific excitement due to its unique characteristics. Rather than random electromagnetic noise, the transmission exhibited narrow bandwidth properties and systematic frequency drift patterns, precisely the signatures expected from intentional technological communications. Predictably, speculation arose regarding potential extraterrestrial origins. However, scientific consensus quickly dismissed alien explanations, attributing the phenomenon to terrestrial radio frequency interference. Subsequently, public interest rapidly diminished as the discovery appeared debunked. Nevertheless, this conventional explanation fails to address several puzzling aspects of the BLC-1 detection. Detailed analysis reveals significant inconsistencies with typical interference patterns. The signal originated from an extremely precise celestial location, specifically Proxima Centauri's coordinates. Standard Earth-based radio interference manifests across broad sky regions or repeats from multiple directional sources. Conversely, BLC-1 demonstrated focused directionality and failed to reappear during subsequent monitoring sessions. This behavioral pattern seems incompatible with human-generated interference sources. If terrestrial equipment truly caused the transmission, why did it appear so spatially concentrated, and why did follow-up observations fail to reproduce the phenomenon? Additionally, the signal failed to match any cataloged satellite or ground-based transmission sources. The observed frequency drift, representing gradual signal changes over time, precisely matches theoretical expectations for transmitters operating from rotating or orbiting planetary bodies, such as a world-circling Proxima Centauri. These critical details received insufficient attention during official analysis. Authorities concluded that BLC-1 resulted from unspecified human-made devices, possibly cellular tower equipment or similar technology, without identifying the actual source. The scientific community accepted this rare, highly focused, singular occurrence as mere coincidental interference. Some researchers acknowledge this incident served as an educational experience for SETI, Search for Extraterrestrial Intelligence, operations, claiming it refined their analytical protocols. While procedural improvements prove valuable, dismissing extraterrestrial possibilities based solely on interference assumptions appears overly convenient and potentially premature. The implications of alien discovery. Imagine awakening to breaking news reports confirming scientists have definitively identified alien life forms or advanced technological signatures on Proxima B. Global media coverage would reach unprecedented levels. Such discoveries would transcend simple astronomical curiosity. They would fundamentally revolutionize humanity's cosmic perspective and self-understanding. Confirmation that biological systems can thrive in environments dramatically different from Earth would demonstrate that our planet's conditions are not uniquely necessary for life development. This realization alone would prove intellectually transformative for human civilization. The implications extend far deeper when considering potential alien technology discoveries. Such findings could completely disrupt existing scientific paradigms, engineering principles, and technological development trajectories. Alternative civilizations might have developed completely novel technological approaches that could inform, inspire, or accelerate human advancement through knowledge exchange or adaptation of their innovations. While these possibilities remain speculative, current scientific efforts continue expanding our investigative capabilities. Researchers continuously push technological boundaries, employing increasingly sophisticated telescopic instruments to conduct remote Proxima B analysis. Their findings progressively add complexity to our understanding of this enigmatic world. Among Proxima B's most intriguing characteristics is its tidally locked rotation. Ensuring one hemisphere maintains permanent stellar orientation while the opposite side experiences eternal darkness. This configuration creates extreme thermal gradients, with one region enduring constant solar bombardment while the other suffers perpetual sub-freezing conditions. Life sustainability under such extreme conditions initially seems impossible. However, a narrow transitional region exists between these temperature extremes, designated the twilight zone or terminator line. This intermediate area might provide stable thermal conditions permitting liquid water existence, and water availability suggests potential biological viability. Furthermore, anomalous electromagnetic emissions detected from the planet's dark hemisphere have prompted scientific speculation regarding their origins. Could these signals represent technological communications from an intelligent civilization? Are we detecting interstellar messages from another sapient species? Advanced observation technologies. Proxima B orbits its red dwarf host star at a distance exceeding 4 light-years from Earth, approximately 25 trillion miles. For perspective, even humanity's fastest spacecraft would require tens of thousands of years to traverse this interstellar distance. Consequently, remote observational study represents our only current analytical option. Traditional telescopic instruments face significant challenges when attempting exoplanet detection, particularly when target worlds orbit in close proximity to bright stellar sources. The observational difficulty resembles efforts to identify a tiny firefly positioned adjacent to an intensely brilliant searchlight. Proxima B presents similar detection challenges due to Proxima Centauri's luminosity overwhelming the planet's reflected light. Advanced technological solutions become essential for meaningful exoplanet research. The James Webb Space Telescope exemplifies next-generation capabilities through its infrared detection systems, enabling distant planetary observation and potential atmospheric composition analysis through spectroscopic techniques. The Harmony instrument, currently under development for the Extremely Large Telescope, ELT, represents another revolutionary advancement. This facility, scheduled for 2028 activation in Chile, will feature the largest telescope mirror construction, approximately 40 meters in diameter. This unprecedented size enables dramatically increased light-gathering capacity and superior image resolution. Scientists anticipate the ELT will achieve groundbreaking observational capabilities, specifically analyzing reflected light from Proxima B to identify potential biosignatures. Spectroscopic examination could detect molecular indicators such as oxygen, carbon dioxide, or water vapor concentrations that might reveal biological activity. A 2025 research study suggests the ELT might distinguish between biologically active and sterile planetary environments within merely 10 observation hours, representing revolutionary analytical advancement. Proxima B maintains its status as humanity's premier candidate for extraterrestrial life detection. Emerging technological capabilities finally provide adequate tools for comprehensive analysis. Should Proxima B possess atmospheric composition, particularly containing biological indicators, the ELT might represent the instrument capable of definitive detection. Such discoveries would finally provide answers to humanity's fundamental question regarding cosmic solitude. Elon Musk's interstellar vision. Elon Musk has achieved another breakthrough following his creation of the world's first commercially viable reusable rocket system through SpaceX, an innovation that completely transformed space transportation economics and accessibility. He now directs attention toward an exoplanetary target beyond our solar system, Proxima B. SpaceX, established in 2002, represented Musk's ambitious entry into aerospace exploration. The company's foundational objective involves reducing space travel costs while increasing mission frequency, ultimately enabling human Mars colonization. Their most significant achievement involved developing rockets capable of multiple launches rather than single-use disposal, analogous to making aircraft reusable instead of discarding them after individual flights. This technological breakthrough saves millions in operational expenses while enabling more ambitious, extended-duration missions. While Musk traditionally focused on Mars exploration, recent developments have captured his attention regarding Proxima Centauri B. Despite its considerable distance, this exoplanet represents relatively close proximity in astronomical terms, practically neighboring territory within our cosmic neighborhood. Proxima B generates significant interest due to its positioning within the Goldilocks zone, the orbital region surrounding a star where temperatures prove optimal for liquid water maintenance. Neither excessive heat nor insufficient warmth, creating conditions where water could exist in liquid form, and water availability suggests potential biological activity. In 2018, NASA scientist Anthony Delano and his research team conducted computational modeling to determine Proxima B's water retention potential. Their findings confirmed viability for surface water reservoirs, prompting Elon Musk's public commentary through social media platforms, describing the planet as practically next door. Advanced modeling studies even suggest Proxima B might harbor oceanic systems reaching 200-kilometer depths, far exceeding Earth's maximum ocean depths. With Musk's continued development of reusable rocket technology and rapidly advancing aerospace capabilities, future scenarios involving SpaceX missions extending beyond satellite deployment, like Starlink orbital networks, toward actual exoplanetary research missions targeting worlds like Proxima B become increasingly plausible. Could this world potentially serve as humanity's second home? Premature conclusions remain inadvisable, yet Musk's interests and SpaceX's technological advancement might eventually enable such ambitious undertakings. The challenge of interstellar travel. The fundamental question emerges. Having identified a potentially habitable exoplanet in Proxima B, with Elon Musk expressing enthusiasm and scientists suggesting possible deep oceanic systems positioned optimally for biological activity, how can humanity actually reach this destination? Distance represents the primary obstacle. Proxima B exists over 40 trillion kilometers from Earth, a measurement that transcends ordinary comprehension of far. Voyager 1, representing humanity's fastest deep space probe, would require 80,000 years to complete this journey, a time span exceeding the entire duration of recorded human history. How could interstellar travel possibly occur within human lifespans? NASA's DEEPIN project, Directed Energy Propulsion for Interstellar Exploration, offers potential solutions. Rather than conventional rocket propulsion, scientists are developing miniaturized spacecraft that could receive acceleration from powerful laser beam systems transmitted from Earth. This concept resembles sailing across space using concentrated light energy instead of atmospheric wind. These ultra-lightweight spacecraft would utilize extremely thin reflective sails that, when struck by intense laser radiation, could achieve unprecedented velocities. Theoretical calculations suggest speeds reaching 20% of light velocity, enabling Proxima B arrival within 20 years instead of 80 millennia. This timeframe falls within human lifespan parameters. Einstein's relativity theory introduces additional fascinating considerations. Time dilation represents a verified physical phenomenon, not science fiction speculation. Essentially, increased velocity causes temporal flow to decelerate relative to stationary observers. Spacecraft crew members traveling toward Proxima B at relativistic speeds would experience time passage more slowly than Earth-based populations. For astronauts aboard such high-velocity craft, subjective journey duration might feel considerably shorter than 20 years. Einstein demonstrated that temporal flow varies based on relative motion, a concept once purely theoretical but now possessing practical space travel applications. GPS satellite systems already incorporate relativistic corrections in their timing mechanisms, representing everyday technological implementation. Current developments spanning SpaceX's reusable rocket systems, NASA's directed energy propulsion research, and Einstein's temporal mechanics collectively transform Proxima B visitation from science fiction speculation toward achievable future reality. Terraforming challenges and solutions. Suppose Elon Musk and NASA successfully achieve Proxima B transportation capabilities. The arrival represents only the beginning of formidable challenges, as the destination environment remains decidedly inhospitable. Human settlement would necessitate comprehensive terraforming operations, essentially redesigning planetary conditions to support terrestrial life. Tidal locking represents the primary environmental obstacle. Proxima B's close proximity to its red dwarf star likely ensures one hemisphere maintains permanent stellar orientation, locked in continuous daylight while the opposite side endures eternal darkness. This configuration creates extreme thermal gradients, scorching heat on one side and sub-freezing conditions on the other. Scientists propose technological solutions for these challenges. Artificial magnetosphere creation could provide protective shielding against stellar radiation and solar flare bombardment. Earth possesses natural magnetic field protection, but Proxima B might lack this crucial atmospheric defense. Human engineering would need to construct this protective barrier artificially. Atmospheric modification represents another essential terraforming component, either through greenhouse gas introduction or artificial cloud system deployment to trap thermal energy and achieve more uniform temperature distribution across planetary regions. The permanently dark hemisphere requires special attention for habitability. Heat transfer systems could move thermal energy from the illuminated to the darkened regions, possibly through extensive underground conduit networks, engineered oceanic circulation patterns, or sophisticated thermal redistribution vents. If oceanic systems exist on Proxima B, they could provide natural assistance through thermal circulation. Saltwater freezes at reduced temperatures, and current systems could naturally distribute warmth throughout planetary regions. Artificial illumination systems could provide light for the dark hemisphere. Powered by solar collection arrays on the illuminated side or orbital mirror installations to supply adequate illumination for agricultural systems and human habitation. Comprehensive terraforming operations would require extensive artificial intelligence assistance. AI systems could manage climate modeling, adjust environmental systems as conditions evolve, and coordinate the construction of human settlement infrastructure through automated manufacturing processes. Terraforming Proxima B represents an enormous undertaking, yet if human colonization is desired, transforming science fiction concepts into practical reality becomes necessary. Evidence of ancient life. A compelling theoretical framework suggests Proxima B might once have supported biological systems. This hypothesis proposes that volcanic activity, oceanic freezing, and extreme temperature fluctuations eliminated all life before the planet became tidally locked, before oceanic systems froze permanently, and before recurring volcanic eruptions created hostile conditions. During earlier epochs, this world might have maintained significantly more hospitable environmental conditions. However, circumstances deteriorated over geological timescales. Proxima B's close stellar proximity subjects one hemisphere to intense thermal bombardment, while the opposite side remains in permanent sub-freezing darkness. Historically, the planet might have experienced more stable climatic patterns, possibly supporting liquid water reservoirs and atmospheric systems sufficiently dense to sustain biological activity. Catastrophic changes likely occurred through volcanic eruption sequences that dramatically altered atmospheric composition. Volcanic systems can release gases, molten rock, and particulate matter capable of completely disrupting planetary atmospheric chemistry, causing extreme temperature variations. Extended volcanic activity could have driven Proxima B's climate into complete instability, with some regions experiencing extreme heat while others plunged into sub-freezing conditions. These volcanic episodes might have been followed by global cooling periods, freezing oceanic systems and rendering planetary conditions nearly impossible for biological sustainability. Previously promising liquid water would have transformed into massive ice sheets covering planetary surfaces. Imagine excavating these frozen oceanic systems, possibly deep beneath ice layers, within protected water pockets isolated from harsh surface conditions. Some biological forms might have survived. This scenario is not entirely implausible. Earth supports life in previously considered impossible environments, such as deep ocean thermal vents where sunlight never penetrates and crushing pressure exists. If humans could access these regions on Proxima B, similar discoveries might await. Perhaps life exists in frozen suspension within oceanic depths, or even preserved biological traces maintained for millions of years. If sufficient warming could be achieved to thaw planetary oceanic systems and restore atmospheric balance, we might witness what Proxima B could have been before volcanic activity and extreme temperatures eliminated previous biological systems. The search for artificial signals. The mysterious luminous emissions detected from Proxima B's dark hemisphere represent phenomena that captivate scientific attention continuously. These light sources do not behave like natural illumination caused by atmospheric interactions or reflected starlight. Their unique characteristics prompt researchers to consider artificial origins, possibly representing alien technological signatures. If this hypothesis proves accurate, humanity might be approaching the discovery of intelligent extraterrestrial life for the first time in history. Not simple microorganisms, not basic water or bacterial systems, but a fully functional technological civilization. What characteristics might such beings possess? Would they resemble humans in any way? Could communication be established? Would they desire contact? These questions transform the discussion from science fiction speculation to urgent scientific investigation. Even if these emissions ultimately receive natural explanations, they reveal how little humanity truly understands about exoplanetary systems. They might disclose previously unknown atmospheric phenomena, unusual chemical processes, or energy sources never before considered. Regardless of origin, these signals provide valuable scientific information. However, significant analytical challenges remain. Proxima B's 4 light-year distance exceeds current technological capabilities for detailed observation. Our most advanced instruments, including the James Webb Space Telescope, achieve remarkable results yet struggle with interstellar distances and interference from Proxima B's host star, a red dwarf prone to solar flare emissions and intense radiation that can disrupt signal detection and complicate accurate planetary analysis. Future technological developments, particularly the Harmony instrument designed for the extremely large telescope, could revolutionize observational capabilities. These next-generation tools might provide superior image resolution and enhanced data collection regarding planetary surface conditions, atmospheric composition, and potential biosignature detection. If these advanced instruments confirm water presence, organic molecular structures, or additional anomalous light emissions, humanity will advance significantly closer to answering the ultimate question: are we alone in the universe?